You might be aware that in quantum mechanics there is something called the uncertainty principle that tells us that if the uncertainty on position is diminished, is decreased, at some point we have to increase the uncertainty on momentum and vice versa. Now, what you may not know, because it's a result of my research project called Assumptions of Physics, is that there is a related uncertainty principle even in classical mechanics. Since most people on YouTube can only keep the attention for 30 seconds, here is the gist. The third law of thermodynamics imposes a lower bound on the entropy. The entropy can be zero, and that's it. It can't be negative. And the zero is reached only when the temperature is zero. Now, if you take that limit and impose it in classical statistical mechanics, you actually get a bound on the uncertainty for classical distribution. So the third law of thermodynamics causes an uncertainty principle in classical mechanics as well. And that's it. So you learn something. Now, for those that instead want to look at things a little bit more deeply and are a little bit skeptical, and which is whenever there is something on the foundational physics, especially in quantum mechanics, always go and look at the detail. Don't just trust some random people on YouTube or even research paper, because everything and the opposite of everything is written. We are going to go and look at the detail of this claim. It shouldn't be that hard to follow. If you know what the variance is, and if you sort of have heard a little bit about entropy, you should be able to follow. The core mathematical derivation requires knowledge of Lagrange multiplier, but even if you don't know what those things are, you can just trust me on the calculation, or trust somebody that you know that knows about Lagrange multiplier. After we've seen all the details, we're going to have a discussion of the significance of the result, especially in the context of quantum mechanics. And if you're interested even in more details, I'm going to leave the link to some papers in the description. So let's get started. So the first thing we should do is review the uncertainty principle. So in quantum mechanics, there is this relationship between the uncertainty on position and uncertainty on momentum in terms of their standard deviation. That tells us that the product of the standard deviation on position and the standard deviation on momentum has to be greater or equal than h bar over 2. Now, one common misconception is that this uncertainty is about the measurement, and it's really much deeper than the measurement. It's really about preparation. Like, you can't even prepare a state that is prepared better than that, because the uncertainty in the mathematical framework is really built into description of the state. So the state, when you specify the state, already has that bound, and you can't do any better. So the idea is, in quantum mechanics you have this uncertainty principle, and the common thinking is that there is no such thing in classical mechanics. The uncertainty of position and the uncertainty of momentum can be arbitrarily low to the point that they can actually be infinitely precise. And so we're gonna think a little bit about this. Is it really the case? Is it really like that? So if we just look at classical mechanics itself, there doesn't seem to be a limit, in the sense that if we take a probability distribution over a single classical degree of freedom, so we have a distribution rho over position and momentum, we can make the uncertainty, we can make the distribution as narrow as we want. So you can imagine that this is a distribution of position and momentum. The lighter colors are the higher values, and you can imagine that we can shrink this into a smaller and smaller region, to the point that we would have a delta Dirac if the distribution was all concentrated at a point. But classical mechanics doesn't really deal with statistics. For that, we need to look at classical statistical mechanics. And in classical statistical mechanics, there is this thing called entropy, which is a physical quantity that is related to uncertainty. And the third law of thermodynamics puts a bound on that entropy, tells us that it cannot be negative. The lower value that it can have is 0, and it can only reach 0 when we are at absolute zero temperature. But the common thinking here seems to be that the entropy for a single state is 0. So if we have shrink everything to a single state, we have 0 of entropy, and so everything is fine. And But is that really the case? So we should actually go and double check this claim. So in statistical mechanics, there are two actually different ways to define entropy. So we want to check what happens in both. The first one is the logarithm of accessible microstate, which is the Boltzmann constant times the logarithm of the number of states. And in this case, we only have one state, and so we have kb logarithm of 1. The logarithm of 1 is 0, and therefore the entropy for a single microstate is 0. So that seems to be fine. And on the other side, we have the Gibbs-Shannon entropy, which is used when you actually have a probability distribution. And this is given by minus kb, the constant is the same, the sum of pi log pi. Now, in this case, if we have just one state, we have 100% probability on just that one state, so we have only one contribution, and that contribution is going to be minus kb 1 logarithm of 1, and again the logarithm of 1 is 0, and therefore we still have 0. And so everything seems to be working, we have one state, and we have 0 entropy. But the problem is that this calculation and this formula works in the discrete case, where when our variable are integers. And phase space is not a discrete space. The variables that we use there are real values, they are continuous variables. And so these equations actually are not the correct one in that case. So which equation do we need to use for, in that case, we need to use a slightly modified version. The logarithm of accessible microstate is the same, except that now w is not the integer that counts the number of points, but it's the phase space volume, a volume of phase space. And if we have a single point, the volume is 0, and therefore the correct computation for the entropy is kb logarithm of 0, and the logarithm of 0 is minus infinity, it's not 0. So we have a different value here. We should confirm when using the Gibbs-Shannon entropy in the continuous case, and that again becomes an integral, the sum becomes an integral, so the function here actually is different. And if we have a probability distribution on a single state on a continuum, we do have this delta Dirac, which is a function, which is a distribution that is 0 everywhere except at a point, which is going to be infinite. So again, since it's 0 everywhere except that point where it's infinite, the contribution is going to be minus kb infinity logarithm of infinity. And logarithm of infinity is infinity, so this expression evaluates to minus infinity. So the entropy, even in the Gibbs-Shannon case, is minus infinity. So the entropy of the single microstate in classical mechanics in phase space is not 0, is actually minus infinity. And this violates the third law by a lot. Okay, so we do seem to have a problem, because we need to constrain ourselves to distributions that have non-negative entropy. So what happens if we do that? So what does the lower bound of 0 entropy tell us about the uncertainty? Well, before proceeding further, we should look at this expression on the continuum and note that here we have W, we said that it's a volume of phase space, so it's in unit of volumes of phase space. The other expression instead has a rho, which is a density over phase space, so it's units of probability over phase space. And the issue is that the argument of a logarithm should be a dimensionless quantity, because it doesn't make sense to exponentiate to something that it's not a dimensionless quantities. If I say 2 to the 3 meters or 5 to the 10 seconds, like those are meaningless, and in the same way the logarithm should be, the argument of the logarithm should be a dimensionless quantity. So we have a problem here. These expressions are not even dimensionally correct. Now, isn't it interesting that people who work on the foundations of physics, you're gonna hear things about hidden variables or branches of the universe and stuff like that. And here we have expressions that are not even dimensionally correct. Things that you study when you are in high school or in first year of university, these things are not correct. But anyway, so what we want to do now is to fix this so that when we get some physics out of the expression, we can actually get something sensible. Because if these things don't even work dimensionally, how can we trust what we take out from those expressions? So to fix this expression, we know that, the functional form actually works. It gives us the correct relationship. So the only thing that we need to do is simply introduce a constant to fix the unit. That's the only thing that we have to do. And so what we simply need to do is that if we have a volume that has units of phase space, we divide it by a constant that represents a volume in phase space such that the units go away and our logarithm is a logarithm of a pure number. And so we can write this constant W0 into two parts. One part is the actual numeric value, and the other part is just one unit in phase space that uses the units given by Q and P. If we do this, we take this and we substitute it here, we can sort of understand a little bit better the unit dependency. What's happening is that this W0 is a pure number because it's just a numeric value. And now we have the logarithm of a sort of the product of two things, and that becomes the sum of the logarithm. And then we can take the inverse of 1 over W0, and that is going to give us minus the logarithm. And so we basically see that this more correct expression is equal to the sloppy expression before that was just simply dropping the units without thinking about them, minus kb logarithm of W0. And what happens is that now this is a constant and it actually changes the zero of the entropy because it's just a constant. And so we can understand that W0 is simply the phase volume that represents zero entropy. So if we had a macro state with a volume that was exactly W0, that would be the zero of the entropy. So the idea that we wouldn't be able to shrink below that volume, because otherwise we would be violating the third law. Something similar we can do for the Gibbs-Shannon entropy. And here, rho was a probability over volume of phase space. And so now we multiply by volume of phase space such that things cancel out. And we just have the logarithm of probability, which is a pure number, and therefore we are fine. And if we do the same trick that we did before, we would get again the logarithm, the sloppy expression that ignores the unit, minus again the same constant as before that just changes the zero entropy. So things are consistent between the two expressions. Now we can note that in principle you could change the units of Q in a way that would rescale this expression, would rescale the W0, and therefore the lower W0, the numeric value of W0 would be 1, and therefore you wouldn't have this term. And so the idea is that you can sort of understand this expression, the sloppy one, as the expression is some kind of natural unit such that volumes, like the unit volumes in phase space, is exactly zero entropy. So basically we can still understand those sloppy expressions as something still meaningful, but that they are only valid in a specific unit system. Now, naturally, if you change the zero, the difference in entropy is still going to be the same. Therefore, and since most of the time you actually are interested in different differences of entropy, that's why most of the calculation done with the sloppy expression are still valid and still work fine. So now that we understood all the details about this, we are ready to actually go and see what the zero bound on entropy tells us about the uncertainty. So we want to find the minimum uncertainty, which will be found at the lowest level of entropy, which is 0. So we want to find a distribution rho that minimizes the product of the variances, and we use the variances instead of the standard deviation so that we don't have this pesky square root to deal with, right? The expression is going to be easier, and since the standard deviation is a positive value, square of the positive value, minimizing the square or minimizing the value is the same. So we want to find the distribution rho that minimizes the product of the variances, given that rho integrates to 1, because it's a probability distribution, it has to integrate to 1, and the entropy of rho is 0, which is the constraint we said before, that's the lowest entropy that we can get. So to do that, we use the Lagrange multipliers. And so if we know and understand that technique, you're going to be able to follow. And if you don't know what that technique is, you kind of have to take my word for it. And that's how it works. So we set up our expression, which is going to be the function that we want to minimize, which is the product of the variances. And we expand the product of the variances as the expectation value of, for example, position minus average position square, and then times rho, because this is how we take the expectation value. And the same thing for sigma p square is going to be p minus the average p all square. And this is the thing that we want to minimize. And now we put the constraint, each with its own multiplier. So the first multiplier is gamma 1. The first constraint is that the total probability has to be equal to 1. So this is the expression that calculates the total probability. And this is the value of the constraint. And the second constraint instead is the Shannon-Gibbs entropy, which we calculate like this, as we saw before. And 0 is the constraint. Okay, so let's proceed with the calculation. First thing that we're going to do is there is this multiplier, and here we have a constant. And again, since we're going to do math now, we want to take those constants away to make our life easier. And so we incorporate the constant in the multiplier, and so we are going to write that lambda 2 is lambda 2 prime times kb. So that way we get rid of kb. And then we're going to expand the W0 so that we again go back to the sloppy expression, and we just have rho logarithm of rho minus the logarithm of W0. Okay, so now we have the mathematical problem nice and set up, and now we can take the variation. So we need to take the variation of the first term. The first term is 2 integrals of rho, so the product of 2 integrals of rho. So we first do the variation of the first, and then the variation of the second. You notice that in the first term here, the only dependence of rho is this one, which is rho itself. So we have the variation of rho times everything else, times q minus average q square, times sigma p square, which is this other term just represented in a shorter, more compact form. And now we have to do the same thing on the other side. So we have sigma q square, which is this term, and times the variation of rho, which we collected here, and then p minus mu p square, which is here. Right? So these are the variations that comes from here. We have the first constraint, and again, the only rho dependence is here, so we just have the variation of rho times lambda 1. Here we have the second constraint, and we have rho log rho, which again is the product of 2 terms, so we make the variation of the first. The variation of the first would be variation of rho, logarithm of rho, times minus lambda 2, so it's this term over here. And the variation of the second, the derivative of logarithm of rho would be 1 over rho. That simplifies with rho. So we just have the variation of rho times minus lambda 2. And so this is the variation. And we want to set this variation to 0. And the only way that we can set this variation to 0, no matter what the variation of rho is if this whole thing is 0. Now note that this term, the term with the logarithm, is the only term that depends on rho. So we take this term, bring it on the other side, and therefore we have lambda 2 logarithm of rho equal to all the rest. Now we take lambda 2 and we bring it down here, so we divide everything by lambda 2. Then we exponentiate, and then we find the solution that rho has to be equal to the exponential of lambda 2 minus lambda 1 minus lambda 2 over 2, and this is just a constant, so it doesn't really matter. This is the term that has the only q dependency, which is going to be a q minus average q square. And this is the term that has the only p dependence, which is p minus mu p square, and everything else is a constant. And the constants are going to be chosen so that we can satisfy a probability that integrates to 1 and that the entropy is 0. So the only thing that is really important here is the functional form. So we have, our distribution is an exponential of position minus average position square, and exponential of momentum minus average momentum squared. And you might recognize this functional form. It's a Gaussian, except we have to put the minus instead of a plus, but that's again fixing, it's a matter of fixing those constants. So let's go back and use the standard expression for a Gaussian, which is going to be 1 over 2 pi sigma q sigma p, and this is simply the normalization constant, such as the integral is going to be 1. And then we're going to have the functional dependency, which is minus position minus average position square over 2 times the variance, and for Q, and then the same thing of P. So this is essentially the product of 2 independent Gaussians. Now, since the entropy is 0, we can go and calculate the entropy to find a bound of sigma Q and sigma P. So the entropy is 0 and the logarithm of 1 is 0. So we have that the entropy has to be equal to kb log 1. And if we go and calculate the entropy with the units correctly, we find that it's kb logarithm of 2 pi e sigma q sigma p over w0. So we have that this part in parentheses has to be equal to 1. And we can take it and we can re-express it like this. So we find that sigma q sigma p is equal to w0 over 2 pi e. And so we find that the Gaussian is the function that minimizes the uncertainty when we have put a minimum of 0 for the entropy. And therefore, this is the minimum certainty that you can ever have in classical mechanics with a distribution that has a non-negative entropy. And so now let's compare that with the quantum uncertainty principle. So in classical mechanics, we find that every classical distribution with non-negative entropy satisfies the sigma q sigma p greater or equal to w0 over 2 pi e. And the equality holds for a Gaussian. In quantum mechanics, we have that every quantum state, and every quantum state has non-negative entropy, and in fact, every pure state has 0 entropy, every wave function has 0 entropy, satisfy the uncertainty principle sigma q sigma p is greater or equal to h bar over 2. And the equality holds for a Gaussian wave packet. So you see there is complete similarity between these two expressions, and that's why I like to call this the classical uncertainty principle. Okay, so let's look at a little bit better how this works in terms of the space of function to have an idea of what we've just seen. So let's suppose we have the space of all possible classical distribution, which is going to be represented here. And in the vertical side, we are going to order them by the entropy, right? So if a distribution here is here, it has entropy 0. If it's here, it's greater than 0. If it's here, lower than 0. And on the horizontal axis, we order them by sigma q sigma p, so the uncertainty. And so what we find is that this is the region of classical distribution because we can't have, for example, a distribution that has a high entropy and low uncertainty, right? So here, just the compute of entropy tells us that there are no functions below this this exponential on this side. But then we have the third law of thermodynamics that comes in and tells us that we can't have anything below the 0. So all these are excluded, and so the only distribution that can exist in classical statistical mechanics are these, are the gray area in the upper quadrant. And when we have this on the dashed line, which is the minimum uncertainty, we have Gaussian distributions. And so this point here is the minimum uncertainty that we can ever have, and that's where it satisfies the equal in the classical uncertainty principle. So what we found essentially is that the lower bound of entropy is responsible of an uncertainty principle in classical mechanics. The converse is not true. Like if we take the space of all distribution and we put a lower bound uncertainty and that's it, we can still go and get arbitrary low negative distribution with arbitrary negative entropy. So you don't get a bound of entropy. So the implication goes only in one direction. And so we can say, I think, conclusively, that the third law of thermodynamics causes the uncertainty principle, at least in classical mechanics, but I think it would make sense to say that that's what's actually happened in quantum mechanics as well. So why do I think this is interesting? First of all, it basically shows that classical mechanics and quantum mechanics are not that different. I think there is this overemphasis of how quantum mechanics is weird and is special, is completely different. And I do think there are a lot of people that sort of like the fact that it's like that, but I really don't think it's helpful. And in fact, through our project and through our approach called reverse physics, we see more and more that there are a lot of things that one would think they are only in quantum mechanics that are already there in classical mechanics. You can have, for example, a classical antiparticle. There is a nice analog that allows you to understand even better what's going on. So if we can debunk this idea that these two theories are completely different, they have nothing to do with each other, I think that only is going to help people understand both of them way better. The second point is that it links the uncertainty principle to some more down-to-earth, tried and true ideas, which are the laws on thermodynamics. And here the idea is that if we understand quantum states as ensemble, as sort of the best ensemble that we can ever prepare, even conceptually, then we can see that the lower bound of entropy causes the uncertainty principle. So again, there is nothing special, there is nothing that wouldn't be anticipated if we think in those terms. So the uncertainty principle becomes something very natural and expected, and not this weird thing that where does it come from? Well, it comes from the third law. The third reason why I think this is interesting is because it tells us in a way why classical mechanics fails. It tells us that classical mechanics inside its framework allows the existence of ensembles that have entropy that is lower than zero and potentially arbitrarily low negative entropy, which of course does not make sense. So one would expect that if we were looking at ensembles that are of low entropy, that's exactly the area where classical mechanics would fail. Classical mechanics wouldn't give us realistic results because the whole model in that region is not realistic. And that's what quantum mechanics is there to fix, because quantum states have a bound of zero entropy, and therefore they are more correct in the description of reality. So I think this is a better way to look at things. I think we need a better way of look at things, and that's why I have this project called Assumptions of Physics. And if you liked these sort of ideas, you're probably going to like other ideas about that we have in the project. So you might look at other videos that I made. I use this channel to sort of popularize some ideas that comes out of my research. If you're interested in our research, I'll put also a link to the website in the description, so feel free to browse around. And if you're still here, I thank you for your attention and for joining me. See you next time.